Welcome back. Today we're going to perform a short circuit analysis based on IEC 6909 standard. IEC 6909 and the associated standards classify short circuit currents according to their magnitudes, maximum and minimum, and fault distances from the generator far and near. Maximum short circuit currents determine equipment ratings, while minimum currents dictate protective device settings. Okay, in IEC short circuit calculations, an equivalent voltage source at the fault location replaces all voltage sources. A voltage factor C, this we're going to discuss in depth later, is applied to adjust the value of the equivalent voltage source for minimum and maximum current calculations. Okay. All machines are represented by their internal impedances. Transformer tap can be set at either the nominal position or at an operating position, and different schemes are available to come of transformer impedance and system voltages if of nominal tap setting exists. System impedances are assumed to be balanced three-phase, and the method of symmetrical components is used for unbalanced fault calculation. Okay, so the singular diagram that what we have in our screen right now, this is taken from my previous project. It's actually is a gas oil separation plant project. Okay, so this is a dual or double radial system. That's why here we have a redundant system here. So here we have a redundant transformer, we have redundant buses. We have bus A, we have bus B. In performing short circuit analysis adopting IEC standard, there should be two separate power grid. Okay? One is for maximum and one is for minimum. Maximum, this is used for the evaluation of equipment ratings. And the minimum, this is for the protective device settings or for the relay settings. If you're going to conduct for maximum short circuit analysis, this circuit breaker here has to be in on position and this circuit breaker here has to be in open position or off position so that the information for the minimum will not be considered. Well, while also for running the minimum short circuit, the CB1 will be open and while the CB2 will be closed. Okay. We have here for the maximum power grid our short circuit rating. Actually, this is the actual value short circuit rating is 1,509 KA. This is the MBA short circuit. While for the minimum, we have here the MBA short circuit is 503 kiloamperes. Okay, so we have here 132 kV bus. Okay, from here down, we have two transformer here rated 4860 MVA on and on off with primary voltage 132 kV is stepped down to 33 kV. Okay, the connection, the vector group is for this transformer is Y in the 1. Okay, so that's why we have a Y connection on the primary side and delta connection on the secondary side. For that, in this project, we provided here the zigzag transformer. Okay, so this zigzag transformer is used as a grounding transformer to create a missing neutral connection from an ungrounded three-phase system to permit the grounding of that neutral to an earth reference point. One of the benefits from this application is that this could perform harmonic mitigation as they can suppress triplet harmonic currents. What are these? These are third, 9, 15, etc. Okay, so from here, we have here the bus A and the bus B for the 33 kV switchgear. This 33 kV switchgear is having a lamp loads. Anyway, I converted this one lamp to be a lamp loads because it's too huge to provide all the information for the other system here. Okay, so we have here actually it's two sets of power transformer. One set is 2.5 MVA, this one and this one. Okay, the primary is 33 kV and the secondary is 0.4 kV. Another set of transformers, also an on and on-off transformer. 8 MVA for on-on and 10 MVA for on-off. The primary voltage is 33 kV and the secondary voltage is 6 kV. This transformer and this transformer. Okay, so from here, we have here a set, a 33 kV switchgear also. This is supplying a set of transformers, okay, and the water injection pump motor. Okay, the rating of the water injection pump motor is 8,500 kilowatts. It's quite huge. That's why it's being rated and connected to 33 kV. Okay, so this transformer is also an on and on-off transformer. 8 MVA for on-on and 10 MVA for on-off. And being stepped down from 33 kV to 6 kV. Okay. Bottom here, we have 6 kV switchgear here. Okay. And it's being having some induction motors and lamp loads. Okay. So before we start running the short circuit analysis, let's check first what because already from all the circuit breakers from here, I have already provided to make it shorter, because if I'm going to show you one by one, it takes time. So here I have already filled up the information for the circuit breaker from 132 kV, 433 kV here, 6 kV, and going down to 400 volts. Okay, so let's check first. Let's check only some of the breakers. For example, here for the 132 kV circuit breaker, let's check this CB3. Okay, double click this one, and let's click the rating of the circuit breaker, high voltage circuit breaker. Okay, I selected the manufacturer. I went here, the library. Okay, so here I selected manufacturer Alstom, and it's rated because this our system voltage here is 132 kV. So there's no exactly 132 kV, sir. Here I selected the next higher one, which is rated 145 kV. So just click OK on this one. Okay. Okay. So here, this is automatically provided by, if you see from here, we have making peak here, and this is AC breaking values. The manufacturer already provided this information because this is required. This is one of the criteria on evaluating the short circuit capacity of the transformer. So the manufacturer itself provided this information already from here. Okay, just click this one. Okay, and also here, aside from the breaking and the making peak, we have also here, this is also initial for our evaluation on the short circuit capacity of the circuit breaker. We have here ITHR value, or we call this one as rated short time withstand current. Okay, so these are the essential values needed when we're going to assess the short circuiting capability of our circuit breaker. This is for the high voltage circuit breaker, the same as the medium voltage circuit breaker. We're going to check that one also, the other breaker, so that we will have the comparison, because for the low voltage the requirement is different. Okay, so here the rated current, even you put here smaller or bigger, there's no issue, because for circuit analysis, this is not necessary. Okay, so just click OK for here, and that is for the 132 kV circuit breaker. Let's check also for the circuit breaker on the 33 kV. Okay, for example, CB10 from here. Okay, let's go to the rating. Okay, and let's go to the library. I choose also here Alstom. Okay, so from here, this is what I have chosen. Okay, since the system voltage is 33 kV, the rated kV for this circuit breaker is 36. The making peak is 62.5 kiloamperes, while the AC breaking peak is 25 kiloamperes. So just click OK. Okay. The same, we have here the ITHR, or the rated short time withstand current of 25 kiloamperes. So this is for the 33 kV switchgear. Okay. So we have done the 132 kV and 33 kV. The same approach also, I have provided the information for the other 33 kV switchgear from here. Okay, bottom here, we have here the 6 kV switchgear. So let's check for CB5. Okay, let's go to rating, double click this rating, and library. Okay, also I selected Alstom. We don't have the exact rated 6 kV here. I chose 7.2 rated kV of the circuit breaker. Okay, the making peak is 161 kiloamperes, while the AC breaking is 6 kiloamperes. Okay, just click OK for this, and we have here the ITHR is 9 kiloamperes. Okay, so later we're going to discuss that one, and we'll show you some reports regarding the breaking, the making, and this ITHR currents, so that you would understand why I'm mentioning these parameters. Okay, so let's just click OK. Okay, so we have done already 132 kV, 33 kV, and 6 kV. How about for the circuit breaker in low voltage in 400 volts? Okay, we have here this here the CB62. This is 400 volts switchgear. Okay, let's double click here and let's see what is inside what we have provided here. Okay, from here, okay, here when we go to the library, okay, just hold on, take a little bit time. Okay, I choose here ABB circuit breaker. Okay, so let's verify the values, the parameters for this breaker. Standard IEC, manufacturer is ABB. Just click OK for this. Okay, from here, see, for low voltage circuit breaker, it's different right now because we have here the service breaking, the ultimate breaking, and the making only, an ITHR, which is somewhat, there's no There's no information here for the DC component, rather the DC component of the short circuit current. Okay, so that's the only difference between low voltage circuit breaker and the medium voltage and high voltage circuit breaker. We still have ITHR here. Okay, so the ITHR value from here is 5 kiloamperes. So just click OK. Okay. Now, this system right now is ready to run for short circuit analysis. But first, let's go to this button here. Okay. Short circuit. Click OK for this. And we have here, but before that, let's go to the edit study case. Okay. So, we have here the faulted buses. Okay. So, ensure that before you run any short circuit analysis, there should be, because this is a prerequisite, there should be always a faulted buses. So, the red one, okay, I'll close this one first. The red one, these are the faulted buses from here. Because once you selected this short circuit, okay, button, and you have already bolted the buses, the buses that being bolted will become red. Okay, see? Okay. So let's go again on to the edit study case. Okay. So from here, we have this information for the faulted buses. Okay. And here, the other side, this is the buses that are not being bolted. Okay. It is mentioned here, don't fault. Okay. Let's go to the standard. Since we're conducting IEC, okay, we have to choose IEC from here. And first, we're going to simulate the maximum short circuit current. From here, this is being the default from ETAP when you're going to conduct maximum short circuit current. For the voltage 1 kV below, the C factor multiplier is 1.05. For the voltages 1 kV, 1.001 kV to 230 kV is 1.1. Since we have, we have 33 kV and 6 kV, and we have also 132 kV, our system is fall to this multiplying factor. Above 230 kV, also the C factor is 1.1. If in case that that this C factor multiplier is different, we can customize by checking from here. Okay, this one we can change the value from here if it is different from what is being recommended by ETAP. Okay, so let's take on maximum from here. Okay, the calculation method is method B, and the Cmax for impedance adjustment in less than 1000 volts, we have here the 1.05 for the plus minus 6% voltage tolerance. Okay, so for the alert, we have this. Okay, so for the critical, this is always 100%. For the marginal, we assign here 95%. Okay, so I think we are okay from here. Let's click OK. Okay, so we have to ensure when running maximum short circuit that this circuit breaker is in closed position, meaning we're going to, and this breaker for the minimum is in open position to ensure that we are running a right, we're using the right parameters from here or using the right value of our short circuit. Okay, so we're going to run and use this run three-phase device duty. Okay, and the second is this one, run line to ground, line to line, line to line to ground, and three-phase faults. But this one, when clicking this button, okay, this is three-phase faults device duty per IEC 60909 standard. Click on this button to perform a three-phase fault study per IEC 60909 standard. This study calculates initial symmetrical RMS, peak, symmetrical and asymmetrical breaking RMS, and steady-state RMS, short-circuit currents under DC offset at faulted buses. Please note that ETAP checks the protective device rated making and breaking capacities against the fault current and flags inadequate devices. Generators and motors are modeled by their positive sequence subtransient reactance. While this button here, this one, okay, this is for the line to ground, line to line, double line to ground, and three-phase faults based on IEC 60909 standard. By clicking this button, to perform line to ground, line to line, double line to ground, and three-phase fault studies per IEC 69 standard, this study calculates initial symmetrical RMS, peak and symmetrical and breaking RMS, and steady-state RMS short circuit currents at faulted buses. Generators are modeled by their positive, negative, and zero sequence reactance, and motors are modeled by their lock rotor impedance. Okay, so let's start first on the run three-phase duty, device duty. Okay, let's click this one. Or CV62 is equal to, there's an error. So let's rectify that error. Okay, time delay, let's provide the time delay here, sample 0.09. Okay. And let's click again this one, duty. Okay. So we have flag here in critical condition. Okay, let's evaluate this flag from here. Okay, so right now, we have this. Okay, so we need to evaluate the CB55 and we're going to check the flag here because in the CB55 here, we have here, for example, the breaking and the thermal energy. Okay, so the actual is rated 7, rating is 7.7 to 7 kiloamperes and it's operating at 175.1%. Okay, so it means what we have initially assigned is less than against the actual short circuit rating in terms of breaking value. Okay, same also for the thermal energy. Here we have also 21. This will be automatically, thermal energy automatically calculated by ETAP. And also for the CB62. So let's go for the CB55, okay, and the CB62. Okay, so this is our CB55 from here. Okay, so this is 55 and 62, right? Okay, so to check that one, for example, if you don't know that information, just go from here. Okay, now you will know which is CB55 here and CB62. So okay, let's go first for the CB. You have here CB55 and the other CB is CB62, right? Okay, so from here The CV62 is this one for the low voltage. Okay, let's change uh, the in the value that we have provided here first on the CV62 for the low voltage. Okay, just double click this one. Okay, and let's go to the rating from here. It was 7 point something, right? Kiloamperes. So let's say, let's provide the information here, 10 kiloamperes. Okay, 10 kiloamperes. And the breaking and the making here, okay, this one is 100 kiloamps. 100 kiloamps because the short circuit rating here is around more than 60 kiloamperes. Okay, and the making usually it's 220%. Okay, let's put here 220. Okay, and click OK for this one. The other one we have an issue is on the breakers 55. Okay, let's go to the rating. Okay, making peak, let's say we provide here 16. Okay, and click OK. Again, we're going to run and check whether what we have provided, new information what we provide right now is sufficient for the actual short circuit current. Let's go here, short circuit, and run again this three-phase device duty. Okay. So right now we have this again an error. Okay, we have on the critical value, right? Okay, on the marginal value we don't have an issue, but we have an issue right now on the issue on the thermal energy as the actual rating is 81 megajoules and it's operating right now at 140.5%, while the other one is 4013. Is huge. So here for CV62 and the CV55. Okay, so this is around 40 times. Okay, and this is around 1.5 times. Okay, so let's again update the information to correct the thermal energy values. Okay, let's close this short circuit analyzer alert view. Okay, let's go again on CB55 and CB62 from here. Okay, so this is our CB65, CB62. Let's go to the rating from here. Okay, so we have here, so let's change this one. This is around, we have around 40 or 50 times, right? So let's check this one, change this one as 50 kiloamperes. Okay, and for this CB, for the CB55 rating, okay, 9, let's say, let's change this one as 20 kiloamperes. Okay, from here. Okay, and let's click OK. So meaning, we use a particular circuit breaker. What the manufacturer provided with us, that particular type, that particular breaker, the thermal energy is shorter. So that's why we update manually in our case. So let's check and run again the three-phase device duty from here, okay? We still have here the issue on CB62. See, 160.5, okay? 160.5, so meaning we need to change again that one. So on the CB62, this is low voltage, you know. From the CB62 from here, it's becoming trial and error because we could, there is the thermal energy, it's mentioned there the exact value, but here, that was calculated by ETAP, but here it's not mentioned from here. It is being calculated by ETAP based on the short time withstand. So still, we change this one into 80 kiloamperes, okay? From here, okay, and run again the short circuit analysis from here. So we don't have flag here anymore. Okay, let's go to the Iec Circuit Analyzer. It means that we have resolved the issue on the thermal energy of the circuit breaker. Okay. Okay, so we have here, this is for, let's go for the high voltage circuit breaker. Okay. You won't see any red flag here or any marginal flag, color magenta, for this high voltage circuit breaker for the 33 kV, for the 132 kV, and for the 6 kV from here. Okay. For the low voltage, also the same. Let's click this, all this information from here. Okay. Also the same. There's no flag from here. Okay. It means there's no abnormalities. For the bus, also from here, nothing is flagged from here. Okay. Nothing flagged because we didn't assign rate, we didn't perform yet the bus bracing on for all the buses. Okay, because we're trying to wait what is the actual symmetrical short circuit current and the peak short circuit current from here. Actually, if you are working in engineering company, normally the verification of the suitability of the device, rather the short circuit breaker, short circuit capacity, will not be performed. Only the short circuit rating of the bus. The designer will only provide the short circuit information, the short circuit study, the short circuit report, so that the manufacturer itself will propose based on the actual short circuit rating on the system. Okay, this is for the bus bar. Okay, so we have here the this I double prime K, this is initial symmetrical short circuit current. IP, this is the peak short circuit current. And the IK here, this is the steady state short circuit current. Normally, if you're going to specify, provide an information on the specification or the data sheet of the circuit breaker, normally, it is based on the short circuit rating capacity only on the and the peak value. Okay, so from here, for example, if you know, for us, for example, we have here the initial symmetrical short circuit current of 6.9 kiloamperes. So means you're going to specify, for example, in the market right now, normally it's rated in 25 kiloamperes, in 31.5 kiloamperes, and we have also 50 kiloamperes for the medium voltage or the high voltage circuit breaker. Okay, for example, here 33 kV. Okay, so here, if you notice from here, okay, for the medium voltage and the high voltage, Okay. The short circuit current is around average around 11 or 12 kiloamperes. So we can propose this one for the short circuit rating of the bus bar to be 25 kiloamperes. For example, 25 kiloamperes in 3 seconds and 25 kiloamperes in 1 second. For the low voltage switchgear, we have here 66 kiloamperes. It's too huge. Imagine 66 around 66.47 kiloamperes. Okay. For this, the equivalent in the market right now, we have 85 kiloamperes. We can propose the busbar rating to be 85 kiloamperes. Okay. So from here, since we have already the idea, the information, we know already the initial symmetrical short circuit current and the peak short circuit current. We can provide this information and run again and simulate sa short circuit calculation. Okay, let's go back to our main signal line diagram. Okay, for the 132 kV switchyard. Okay, we can provide here because we are proposing short circuit current on the bus to be 25 kiloamperes. The peak normally is for the medium voltage is normally 260 percent bigger than the short circuit rating of on the bus bar. Okay, so if we are going to propose 25 kiloamperes, the peak will be 65 kiloamperes from here. This is the standard value from the market. Okay, 65. Okay, and also for the 33 kV switchgear. Okay, if we are going to propose the short circuit current of the bus bar to be 25 kiloamperes, okay, the peak for this one is also 65 kiloamperes. Okay, let's put here 65. So here we can conclude that for the high voltage and the medium voltage switchgear buses, the peak would be we can propose all 65 kiloamperes from here. Okay, so here the rating also is 65. Okay, and this 33 kV, let's change this one into 65 as well. Okay, on the other side, on the bus B, the rating to be 65 kiloamperes. Okay, another 6 kV here to be 65 kiloamperes. Okay, on the other side, 6 kV here to be 65 kiloamperes. Okay, and here downstream 6 kV bus also to be 65 kiloamperes, and the other bus is 65 kiloamperes. Okay, so we have done the high voltage and medium voltage buses. We'll go on the 400 volt bus or the low voltage switchgear. Okay, so let's go to the rating from here. Okay, here, since we are proposing here 85 kiloamperes short circuit rating of the bus, okay, the peak for that one, for the low voltage, normally 220% higher. Okay, so it means here, the peak value to be 187 kiloamperes. The same on the other side, 400 volt switchgear. Okay, the rating to be 187 kiloamperes. Okay, so from here, okay, so before running again the short circuit analysis, let's check the report manager before we updated our buses. Okay, So this is the report manager information from here. This is before performing the busbar bracing. Okay? So here, see, we have here 432 kV switchyard. We have here for the 33 kV switchgear. We have here only the information for the initial symmetrical short circuit current, okay, for this bus, and the information for the peak short circuit current. Here, this bus, this information of the making peak is empty. Okay, so this is the information, this is the data before we provided the information on the bus. Okay, and here also, if you check from here, this, for example, for the 33 kV, the CB4 or the CB10, let's say for the CB10, okay, the device capacity is being measured by their making peak. Okay, this is IB, this is symmetrical short circuit breaking current. Okay, this is the asymmetrical, okay, short circuit breaking current. IDC, the DC component of the short circuit current. Okay, so meaning we have 4 parameters here for the device capacity, and this is, see, and this is the value that we have here, and this is the actual short circuit current for the IP, for the IB, symmetrical and asymmetrical, and IDC. So from here, if you, in your screen, we don't have the font has not changed into any other color, into red or any other color. Meaning, what we have proposed here is sufficient enough for the actual short circuit current. For example, for this breaker CB10, our making peak is 62.5 kiloamperes. But the actual peak value, okay, short circuit current peak is 21.712. Here, we propose 25 kiloamperes for our peak breaking current, short circuit breaking current. Here, the actual is 7.407 kiloamperes. The symmetrical one, we have here 26090 kiloamperes, and we have here 9.21 kiloamperes. This DC component, this is we have here, this is calculated by ETAP automatically, and we don't provide this information. We have here the device capacity is 7.463 kiloamperes, and the actual is 5.481 kiloamperes. So everything what we have proposed here is sufficient enough to handle the actual short circuit current. This is the first parameters for the device capacity of the circuit breaker. Same this one, for this information is the same for the high voltage circuit breaker. We have here 132 kV, the medium voltage 33 kV, and also from here the 6 kV. But for the low voltage, okay, from here, for the low voltage, we have here IDC is not part of the low voltage. Okay, for the low voltage is considering only the making peak, the IB symmetrical or the breaking current symmetrical, the breaking current asymmetrical, and also the DC component of the short circuit current only being considered. So that's only the difference between the medium voltage high voltage circuit breaker against the low voltage circuit breaker. Okay, so let's go back to our single line diagram and let's check the busbar bracing from here. Let's run the 3-phase device duty. Okay. Okay, so let's check our report manager right now. Okay, this is the report manager. This is after we provided the bus bracing. Okay, so we have here, let's go to the information regarding the bus. Okay, okay, so we have here, for example, on the 33 kV switchgear, okay, the actual peak value is 21.712 kiloamperes. And what we have proposed here is 65 kiloamperes. This is the same for all the all the medium voltage switchgear and the high voltage switchgear. Okay, for the low voltage switchgear, here, this is will go down. Okay, we have here, okay, the actual peak is too high. Imagine the actual peak short circuit current is 169.22, and we have here what we have proposed is 187 kiloamperes. So right now, if you see from here, you don't see any change. The font color has not been changed. This is ensuring, it means that what we have proposed, the device capacity for our breakers, for our buses, is sufficient enough for the actual short circuit current. Okay, so we have done here the maximum short circuit current. Now we're going to perform the minimum short circuit current analysis. For that, this one, we need to open this, okay, this breaker, okay. Open this one, this is open, and this one we need to close this circuit breaker. Okay, close this circuit breaker from here. Okay, okay, now let's go to the Iec study case. Okay, going to the standard. Now the short circuit current from here, we're going to choose or select the minimum, meaning this is excluding duty calculation. So the purpose for this one, we'll just calculate the short circuit because we're going to use these values for our relay settings. So that's why from here, let's click OK on this. See here, the duty is off. So you cannot simulate the three-phase duty, device duty from here. You can simulate only directly from here. This one, run LG, line to ground, line to line, line to this three-phase force from here. Okay, so by clicking this one, okay, so we have this information, okay, and let's visit the report manager we have here. Okay, okay, so we can have the comparison right now. Okay, so this is the minimum short circuit analysis. We're going to compare against the maximum short circuit analysis. For example, okay, for the 33 kV bus, okay, the initial for the 33 kV bus, the example for this one, the initial short circuit current is 7.676 kiloamperes. But we're going, this is for the maximum short circuit current calculation or analysis. But for the minimum short circuit analysis, for the 33 kV bus, the actual initial symmetrical short circuit current is only, this is for the three-phase, is only 4.293 kiloamperes. Okay, so this is the information from here. The information from here is used for the relay settings. It is not used, this is not used for the device capacity